Howdy, it's Mr. Russell. Enough with those old guys that worked on chemistry a long time ago. Let's talk about the modern view of atomic structure. We know that there's a proton, electron, and neutron. We know the proton has a positive one charge, the electron has a negative one charge, and the neutron has a charge of 0. We also know that they also have they also have mass. Protons and neutrons have the same mass. The only difference is their charges, but the electron has a very teeny tiny amount of mass. But most people consider it to be negligible, so small that it's negligible, but it does have something. Proton has most of it. This is a larger number than this number. The nucleus is very teeny tiny, so tiny that if the electron was a mile away in a hydrogen atom, the nucleus would still only be the tip of a pen. It would be very, very tiny. And that's the only thing the nucleus really contributes is the identity and the actual mass. The electrons contribute the behavior, where the bonding. The bonding will always happen with the electrons. That's the magic that happens. An isotope is something that has a different number of same number of protons but different numbers of neutrons. You'll see this nuclear notation where you have the symbol here and the mass number on top and the atomic number on bottom. The atomic number is just the number of protons. The mass number is the number of protons plus neutrons. And if in a neutral atom, the number of protons will equal the number of electrons. If it's an ion, you're going to be missing an electron, or you're going to be heavy in electron, whether if it's a positive or negative ion. So let's get some practice. Using squares to represent protons, triangles to represent neutrons, and circles to represent electrons, draw representations of a carbon-12 nucleus and a carbon-14 nucleus in these circles. Did you draw any electrons? You shouldn't have, because I told you to draw the nucleus. So in this one, in the carbon-12, you would need 6 squares and 6 triangles, and in the carbon-14, you would need 6 squares and 8 triangles. Let's identify the types of bonds that we could have. The first one is the covalent bond, where the electrons are actually shared in between. When I say shared, I mean that hydrogen only has 1 electron. It would like to have 2, so it decides to share its 1 electron with oxygen, so that oxygen will share an electron with hydrogen. That way, if they mutually share theirs, hydrogen now has 2 electrons, since one of it belongs originally to itself, but it is now kind of shared one with oxygen. It's a give and take relationship kind of thing. We can show covalent bonds in 3 different models. The Lewis structure here with the dots representing lone pairs on the top. You can draw the ball and stick model, the sticks indicate the bonds, but this is the most accurate model, where they're more like just kind of globs that are onto each other. This shows the uncertainty of the electron cloud as they bond to each other. We'll also need to know what an ion is. An ion is something that has a charge. So if it's heavy in electron or light in electron, it will be called an ion. Remember, cations are positive because a cat has paws, so it's positive. And that means that it has actually lost an electron. It's light 1 electron. Anions are negative because they have gained an electron. Chlorine will actually tend to gain an electron just so it can fill its outer shell. That's why that will happen. When these ions are actually attracted to each other, when when these ions are there, they will actually tend to attract to each other because opposite charges tend to attract. That has a special name called electrostatic or Coulombic attraction. There's a smart guy named Coulomb came up with the idea of the distances between the molecules is related to their charges. Just like two balloons that repel towards away from each other, that would be Coulombic repulsion. If they were like charges, they would attract to each other. I'm sorry, if they were opposite charges, they would attract to each other. That would be a Coulombic attraction. That's what will hold the positive and negative ions together in this ionic bond. Pause and read this question. See if you can draw two formula units of A2B and two formula units of CD. Is this what you get? Whoa, so if you need two formula units of this, of my molecular bond or my covalent bond, then you would have two exact copies. This is the right answer, right way to do it, and the only right way to do it. In this one, these I've drawn two formula unit here. Here's one formula unit, but here's another formula unit. Those are two formula units. I've also drawn some extra ones in here. Remember the problem said draw at least two? The reason why these are happening is because they're aligning themselves just right. If the C's were positive and the D's were negative, then that means that this would be a negative here. This would be a negative, and then this could be a positive as well. So the positives and the negatives can still attract to each other that way. That's how they'll align, and you'll get these crystal forming structures. That happens with salts, and that's why salts are crystals. We'll have to get familiar with the periodic table here. Remember that anything, the metals are always found, the metals are always found on the left side. Oh, my picture's small. On the left side of the periodic table, and the nonmetals are on the right side. Anything that touches the staircase, except for aluminum, is going to be a metalloid. So boron, silicon, germanium, astatine, antimony, all of those are metalloids. Aluminum is a metal, okay? Vertical columns are called groups, and horizontal columns are called horizontal rows are called periods. That is all I have for y'all. Thanks for watching.